At first, I thought it was just another comet, faint, distant, forgettable. Then I saw the dates, the orbit, and the light, and the feeling that something wasn't lining up refused to go away. When 3I Atlas was first logged on 1st of July 2025 by the Atlas survey in Rio Hurtado, Chile, it looked ordinary in the way all new sky notes do, a moving point barely brighter than the background noise. But the follow-ups told a different story. The trajectory was hyperbolic, the speed consistent with a visitor that doesn't owe allegiance to our sun, and the designation came quickly, the third confirmed interstellar object after Oumuamua and 2I Borisov. That much is secure. The discovery circulars and early reports are unambiguous about where, when, and by whom it was found. From there, the timeline is straightforward. The path would carry it to perihelion near 30th October 2025, still well outside Earth's lane, with the closest Earth distance safely beyond 1 AU. No threat, no drama, at least not the cinematic kind. But safe and far doesn't mean simple. As the orbit refined, instruments started to pry into its chemistry and behavior. That's where the questions began to multiply. On a cold screen, the first hints of color are just numbers, filter counts and signal ratios, but color has a way of becoming a story. In mid-September, long exposure images during deep darkness showed a distinct green hue in the coma, the kind of tone that, in comets, we usually trace to diatomic carbon, C2 fluorescing under solar ultraviolet light. That is the textbook explanation, and it fits a lot of comets we've seen. Several observers highlighted exactly that, classic C2 emission, the familiar blue-green signature that tells us carbon pairs are being pumped and re-radiating. But other analyses hinted that the balance might be off, C2 weaker than expected compared with other species, the kind of profile that in comet taxonomies gets called C2 depleted. Those labels are early and cautious, and they don't always survive better spectra. Still, the suggestion alone was enough to slow me down and look twice. If the color is strong but the canonical molecule is scarce, what's doing the heavy lifting? Is it simply measurement limits from different apertures and resolutions, or are we watching chemistry that doesn't map neatly to our usual playbook? For now, both possibilities are on the table. The infrared story grew louder. JWST spectra taken inbound showed a coma dominated by carbon dioxide with water present, but, by comparison, subdued, an unusual ratio by solar system standards. CO2 isn't rare in comets, but CO2 outpacing H2O by this much at several astronomical units is the kind of result that earns a double take in team meetings. One interpretation is formation. Perhaps this nucleus assembled near the CO2 ice line in a different protoplanetary disk. Another is processing. Billions of years in interstellar space can harden the outer layers, alter volatiles, and gate what reaches the coma first as sunlight warms the surface. Both explanations are conservative. Both are consistent with what JWST actually saw. Neither requires exotic physics. Then there were the metals. Reports surfaced of nickel vapor detected unusually far from the sun, distances where metal atoms shouldn't be liberated easily by heat alone. Nickel lines have been seen in solar system comets before, but typically closer in. Catching them early is a surprise that points to either efficient non-thermal release mechanisms or microenvironments on or near the nucleus that don't care about our rules of thumb. I've learned not to overread single detections, but unexpected nickel is the kind of phrase that lingers in a notebook margin. The dynamics, in contrast, have been refreshingly sober. No dramatic non-gravitational acceleration has been confirmed that would force us into a corner. It's shedding dust, it's building a coma, and its sunward motion is behaving the way celestial mechanics says it should. Some public commentary leans hard into speculation, alien sails, controlled course corrections, but the ephemerides don't demand any of that. They demand patience. If low-level outgassing tugs are there, they'll appear as the signal-to-noise climbs post-perihelion. For now, gravity does most of the explaining, and yet I can't ignore the coincidences that invite second looks. The first widely shared green images arrived during an eclipse-darkened window, when the sky background was at its most forgiving, useful for detection, but also a reminder that selection effects can write half our narratives. Some spectra suggest normalcy too, others lean toward depletion. JWST says CO2 is dominant, which feels consistent with an irradiated crust that has been rewired by cosmic rays across unimaginable time. Each of these facts can stand on its own. Together, they sketch an object that is ordinary in its interstellar status and oddly specific in its chemistry. Is that simply the diversity we should expect from other star systems? Or is there a bias in what we can currently measure? And when? Several observers, speaking off the record when their preliminary plots still carried red stamps, told me the same thing in different words. The data aren't contradictory so much as incomplete. Apertures, slits, phases, heliocentric distance, change any of them and you can change the apparent comet you're looking at. A green coma with ordinary physics on Monday can look chemically peculiar by Thursday if your wavelength coverage and geometry move. That's not a conspiracy. It's a lesson in how easily our instruments and vantage points become part of the experiment. So I keep my notebook open and my language careful. 3I Atlas is an interstellar comet discovered on 1st July 2025 by the Atlas Network. It passed perihelion around 30th October 2025 at roughly 1.4 AU. It poses no threat to Earth. The coma exhibits a green hue that, in many comets, is linked to diatomic carbon, but early results have floated the possibility of relative C2 weakness. JWST found an unusually CO2-rich gas environment. There are claims of early nickel emission far from the Sun that merit replication. Those are the facts as they stand tonight. The rest is interpretation, and that is always provisional. What's missing are the clean, long-time series and the cross-calibrated spectra that stitch this into a single picture. Why did the first strong color reports arrive under eclipse-level darkness? Would we have called the hue the same in a brighter sky? If C2 is genuinely low at times, what molecule or process is carrying the green, and does that shift with distance? And if nickel is truly present this far out, which release pathway, photochemistry, fragmentation, electrostatic lifting, got it there? No one can answer all of that yet. Whether these are coincidences of geometry and timing or the first notes of a new class of interstellar chemistry, I'll let you decide. For now, the truth sits between the spectra and the silence, and my next questions will have to wait until the comet turns back into the morning sky. I ended part 1 with a list of facts and a handful of missing threads. What came next were the weeks when the comet slipped behind the Sun from our point of view, and the only way forward was to listen to instruments that could see what we couldn't. As 3I Atlas approached perihelion around 30th October 2025, it went to solar conjunction, effectively hidden in the Sun's glare from Earth. That geometry was expected. It meant the key moment would pass with ground-based telescopes largely sidelined, and any clean detections would have to come from spacecraft or special vantage points. NASA's overview had already set the stage, closest to the Sun at roughly 1.4 AU, no threat to Earth, and a post-perihelion return to the morning sky in early November. The logic held, and so did the dates. In the run-up, the most useful chemistry still came from spectra taken further out. The headline remained stubborn and striking, a CO2-dominated coma, with water present but subordinate. The James Webb team quantified it, CO2 to H2O on the order of 8 to 1, among the highest ratios ever measured, far above what we'd predict at those solar distances for typical comets. You can tell different physical stories from that number: formation near a CO2 snowline in another protoplanetary disk, or surface processing by deep time irradiation in interstellar space. But whichever path you take, you start from the same anchor. The ratio is real, and it is unusual. Closer to perihelion, another thread firmed up. Multiple teams reported the onset of CN emission and, more controversially for our expectations, the scarcity of classic carbon chain signals. In plain terms, 3I Atlas looked C2 depleted by comet taxonomy standards. The C2 to CN ratio so low that it placed the object among the most carbon chain poor comets on record. That label isn't drama, it's bookkeeping, but it matters because a greenish coma without the usual C2 backbone forces you to ask what mixture of gases and dust is carrying the color and whether that mix shifts with lighting and distance. The cautious conclusion from those pre-perihelion spectra was simple. Whatever 3I Atlas is doing, it is not a textbook copy of our average long-period visitor. Then came the metals. High-resolution observations with large telescopes pulled out neutral nickel lines repeatedly at heliocentric distances where nothing about thermal physics makes nickel easy to free. Iron was elusive by comparison, detected only later and weaker, which left the Nephi balance skewed in a way that raised eyebrows in more than one data meeting. One VLT study went as far as modeling the release via volatile carbonyls like NiCO4 and FeCO.5 to explain how metals could appear so far out, an inference that will need replication but fits the line intensities better than sublimating rocks ever could. It's not proof of anything exotic, it's an attempt to make sense of hard spectra. If you're looking for the twist where the trajectory stops obeying gravity, this isn't it, at least not yet. The public ephemerides and institutional summaries remain consistent with a gravitational course, with any non-gravitational outgassing forces still below the threshold that would demand a rewrite. The forecasts about visibility after conjunction, reappearing before sunrise in November and likely fading through December as it climbs away, also line up with practical observing notes shared across the community. The science is patient even when the attention span online isn't. And still, there were moments that felt like investigative hooks rather than tidy conclusions. A spacecraft team hinted, off the record, that coronagraph data might have caught a brief sunward jet near closest approach, a feature just large enough to register above the background but too compact to characterize without better cadence. Another observer pointed to Mars orbiter planning notes, suggesting that instruments at the red planet could have had the right phase angle to sniff the coma as 3I Atlas skimmed past on the far side of the Sun. Whether those datasets will materialize into public, peer-reviewed results is an open question, but the geometry makes the idea plausible. We knew from the start that perihelion would be a test of patience. The harder part has been knitting chemistry into mechanism. If CO2 truly outruns H2O by such a wide margin, is that a surface story, crusts, mantles, and microporosity, or a primordial one wired in at birth in a colder, more carbon-rich zone of a foreign disk? If CN lights up while C2 stays suppressed, is the carbon chain poverty telling us about parent molecules that never formed, or about destruction pathways that erase them before we can see them? And if nickel really concentrates close to the nucleus while iron lags, are we watching a volatility lottery whose rules we only half understand? The papers sketch careful answers. The residuals leave enough room for doubt to keep notebooks open. A few coincidences persist. The first strong claims of C2 depletion came from setups with limited spectral windows and different apertures. Subsequent detections of CN arrived as the phase angle changed, which can bias what we perceive as dominant. The nickel detections themselves are secure, but the mix of instruments and resolutions makes cross-calibration slow. And throughout, the sun sat in the way at the very moment we most wanted a clean, uninterrupted look. Is that just how sky geometry treats us, or did we miss a short-lived episode that would have stitched these pieces together? No one can say yet. What I can say is this. The picture that emerges after conjunction is not a sensational one. It's a disciplined mosaic. 3A Atlas is back in the dawn, dim but traceable, with a chemistry that keeps leaning away from solar system averages and a metal signature that refuses to be conveniently thermal. It remains a natural comet, interstellar by orbit and idiosyncratic by composition. Whether its peculiarities are fingerprints of its birth or scars from its exile is the question that will drive the next set of spectra. For now, I'm keeping a short list on the first page of my field book. Confirm the CO2 SAR H2O ratio post-perihelion with independent instruments. Watch the CN and C2 balance as the heliocentric distance grows. Test the Naife trend against different apertures and models, and see what, if anything, the spacecraft teams will publish from the window we couldn't see. Whether those threads tie into a neat knot or fray into something stranger, I'll let you decide. The comet is back in the morning sky. The silence is thinner. The real answers are somewhere between the lines of the next spectrum. From part 2, you'll remember the chemistry that wouldn't sit still. CO2 outpacing water, carbon chains on mute, and nickel where heat alone shouldn't reach. When the comet finally slipped out from the sun's glare, we had a second chance to see whether those threads would hold. At dawn, the sky became useful again. The comet crept back into the morning, faint but measurable, and the first amateur frames, grainy, careful, honest, matched what the ephemerids had promised all along. No sudden course change, no theatrical surge, just a returning visitor that rewarded patient exposure and a steady mount. That, in its way, was a result. If non-gravitational forces were present, they were small enough to hide inside the noise of ordinary outgassing. The easier story, gravity first, chemistry to taste, remained intact. The chemistry, however, kept pressing its case. The Webb spectra taken inbound had already pinned the headline, a coma where CO2 dominated and H2O bent the knee. Numbers like 8 to 1 don't appear by accident. They point to a nucleus that either formed in a colder CO2-favored nursery or spent so long in interstellar exile that its upper layers were rewired by radiation, porosity, and crust conspiring to throttle water while letting carbon dioxide through. Neither scenario is exotic. Both are consistent with a surface that does not behave like the ones we trained on inside our own system, and as the comet brightened toward and past perihelion, the practical consequence of that imbalance became obvious in the observing notes. The lines we're used to leaning on weren't the lines doing the loudest talking. Reports of CN emission recovered as geometry improved, but the classic carbon chain backbone, C2, stayed stubbornly quiet in several setups. Calling a comet C2 depleted is not a verdict. It's a taxonomy tag, a way to say that the familiar ratio of C2 to CN has slid to the shallow end of the distribution. Yet the label matters, because a greenish coma without a strong C2 contribution forces you to ask what else might be sharing the load. Depending on slit width and phase angle, dust continuum can masquerade as color, other molecules can shoulder some of the fluorescence, and transient jets can bias what a single spectrum thinks is typical. In other words, we might not be measuring the comet so much as the intersection of our instrument and its moment. The metals were the least willing to fit into a convenient box. Nickel lines turned up again in high-resolution optical work. secure enough to survive skeptical checks, awkward enough to provoke more modeling than any observer budgets for. Iron, by comparison, played hard to get. A Nephe pattern like that invites chemical roots you don't need close-in heat to run. Volatile carbonyls are one option. Nickel and iron bound to carbon monoxide, photochemically liberated far from the sun into atoms we can see. It's an unromantic idea that nonetheless respects the spectra and leaves the door open for the mix to change with illumination and time. I wrote carbonyl in the margin twice, then underlined it when a second team's reduction nudged the same way. All of this happened while the geometry imposed its own discipline. We lost the exact perihelion window behind the sun. We reclaimed the weeks after at low altitudes before sunrise. If there was a brief sunward jet near closest approach, one coronagraph team hinted at a compact feature just above the background, we would likely see only the aftermath, faint asymmetries in the inner coma, subtle changes in line widths, an evaporating signature that refuses to repeat on command. A Mars orbit instrument may have had the phase angle to glimpse more. Whether those data leave the planning notes and enter the literature is, for now, a diplomatic question as much as a scientific one. Still, the mosaic sharpened. Hubble's imaging pinned the morphology with the kind of context that long slits can't provide, and ground-based ephemerides kept matching the sky to the spreadsheet with a quiet confidence that undercuts the louder speculations. The amateur frames stitched into time-lapse made a separate point. This isn't an apparition that rewards urgency, it rewards habit. Night after night, the same field slowly became a different one. I tried to knit the threads into mechanism. If CO2 leads because the near surface is mechanically hardened, that tells us something about microporosity, grain size, and thermal skin depth. If CN emerges while C2 stays muted, it hints at parent molecules that either never accumulated in bulk or are selectively destroyed on their way out. If nickel is easier to see than iron, perhaps we're looking at differences in binding, volatility, or photolysis cross-sections that legacy comet models treat as footnotes. None of these thoughts require a contrarian universe. They require better cadence, more consistent apertures, and the humility to accept that a spectrum taken on Monday is not obliged to rhyme with one taken on Thursday. And there were the hooks I couldn't shake. Why did the first confident claims of carbon chain depletion come from instruments with the narrowest windows? Do broader band setups dilute a real signal or average away a geometric bias? If nickel truly appears before iron at these distances, is that a genuine chemical asymmetry or the artifact of a sensitivity edge we haven't fully mapped? Who, if anyone, had a clean look during conjunction, and what did their pipelines decide not to show? These are not accusations, they're reminders that the word complete arrives late in any honest dataset. By the time the comet rose higher before dawn, the community's tone had settled. No one credible was claiming wild non-gravitational antics. No one careful was denying that the composition leaned away from solar system norms. The epistemic middle, where confidence bars are drawn in pencil and updated in pen, was doing the ordinary work of science. My field book for the next run kept the to-do list short and sharp. Replicate the CO2-H2O ratio with independent instruments, map CN and C2 with the same geometry over multiple mornings, chase the Nephe trend with cross-calibrated resolutions, archive everything in a way a stranger could reproduce. Whether those lines close the inference gap or open a larger one, I'll let you decide. For now, 3i Atlas is exactly where the calculations put it, and exactly as strange as the spectra allow. The rest lives in the blank space between sunrise and the next exposure, where certainty is scarce and the numbers still don't behave the way we expect. The last time I wrote, 3i Atlas had just reappeared from behind the sun, dim, disciplined, and obstinately strange. Now it was drifting outward again, retreating into the cold, carrying with it more questions than it had answered. As the phase angle widened and solar illumination softened, the comet's coma began to lose its color contrast. The once green hue thinned into pale gray, a change many called expected, but few could explain precisely. If the C2 bands were truly weak, then the fading was a straightforward consequence of geometry and chemistry. If not, perhaps it was the dust continuum washing out the emission lines. The challenge was no longer about detection, it was about interpretation. Every measurement looked clean, and yet none aligned completely with the previous one. Spectra taken in late November confirmed the earlier carbon chain depletion. The C2 to CN ratio remained low, pushing 3i Atlas deeper into the C2 poor category, a designation shared by only a small fraction of known comets. Those comets, interestingly, tend to come from the Oort cloud, pristine, untouched by the inner solar system. But 3i Atlas was not one of ours. That single fact made the analogy uneasy. Why would an interstellar body show the same chemical pattern as the most isolated members of our own system? Some proposed a common history of radiation damage in the interstellar medium. Others whispered about convergent chemistry where similar environments sculpt similar outcomes. Either way, the pattern refused to vanish. Infrared observations after perihelion hinted that CO2 still dominated the gas output, though the ratio appeared to narrow. If true, that meant water was finally catching up as sunlight penetrated deeper layers of the nucleus. A simple thermal model could explain it. The top crust burned through its CO2 stockpile first, then the subsurface ice began to vent H2O as the comet receded. But not everyone was satisfied with that narrative. One group noted that the CO2 H2O curve seemed too flat to be just temperature driven. Another pointed to outburst like fluctuations in the photometry, small, brief brightening events that didn't fit a smooth sublimation curve. Nothing catastrophic, but enough to make the data whisper of a structure beneath the crust more complicated than the uniform blocks we draw in textbooks. Nickel remained the wild card. The early detections had held up. Subsequent spectra found the same lines, still visible at unexpectedly large heliocentric distances. Iron again trailed behind, and the imbalance between the two metals began to look less like an accident and more like a clue. The carbonyl hypothesis, NiCO4 and FeCO5 photolysis, still matched the numbers best, but it carried its own questions. Where did those molecules come from, and how did they survive eons in deep space? Could they have condensed in the original protoplanetary disk before the comet was ejected, frozen in like fossils from another star? No one could say. Each attempt to model the chemistry produced solutions that fit one observation and broke three others. When the comet moved beyond 2 AU from the Sun, its brightness dropped below the comfort zone of most telescopes. The amateurs kept trying, stacking exposures into faint whispers of motion against the star field. Those images told a different story, not about composition, but about behavior. The coma stayed symmetrical, the tail weak but steady, no fragmentation, no jets. For an object that had carried so much theoretical turbulence, its actual dynamics were disarmingly calm. The truth, as always, was quieter than the headlines. Still, silence has a way of amplifying small anomalies. In early December, a few radar facilities attempted long baseline observations, hoping to resolve the nucleus or at least catch echoes of its dust. The results were inconclusive: weak signals, high uncertainty. Yet one data set contained a timing irregularity, a microsecond shift that didn't line up with the predicted ephemeris. The offset was smaller than the measurement error, but it drew attention. Could it be a calibration artifact? Almost certainly. But someone in the analysis thread typed a single sentence that stayed with me. If it's not, then the nucleus may be tumbling faster than assumed. A faster tumble would explain some of the sporadic outgassing patterns, though not all. I wrote it in the margin with a question mark. Maybe rotation was the hidden variable in this puzzle, the unseen metronome behind the shifting chemistry. Days later, another clue surfaced. Observations from a small European observatory noted faint polarization changes in the coma dust, slight but systematic. Polarization often hints at grain size and alignment. In comets, it can betray structure in the ejected material. If true, it might mean that dust jets existed after all, just too faint or too transient to see directly. Together with the suspected rotational variation, it painted a picture not of chaos, but of subtle order. An engine turning quietly, shaping its emissions with mechanical rhythm rather than random outbursts. I find that detail strangely comforting. The more we look, the more 3i Atlas behaves like nature's experiment in patience. Nothing spectacular, yet full of coherence beneath the noise. The comet doesn't need to be alien to be extraordinary. It only needs to remind us how much we still project our own expectations onto the sky. It's moving away now, toward the darkness where only the most determined lenses can follow. Whether it will ever pass close enough again for another look, no one knows. Maybe by the time we see it next, it will have drifted so far that its own gases have frozen again into silence. For now, I'm left with a notebook filled with half answers. Why nickel more than iron? Why water after carbon dioxide? Why a green hue that refuses to name its source? And a final question that keeps echoing in my head, one that every observer eventually learns to ask: what if the mystery isn't in the data at all, but in the way we choose to look? From part 4, you'll remember the outward drift, color thinning, carbon chains still quiet, nickel refusing to leave the stage. I kept watching because the final act of a comet often says more about its origin than the entrance ever can. By December's end, the geometry turned unforgiving. Low altitude, short dawn windows, and a sky that punished hesitation. Yet the plots accumulated in the same patient handwriting. The orbit stayed obedient. No dramatic non-gravitational kink. No late surprise to rescue bold theories. If outgassing pushed at all, it did so in the margins, small enough to hide within the fit of a standard comet model. That silence felt honest. It told me the object didn't need theatrics to be interesting. It needed time. The chemistry still spoke, if more softly. Post-perihelion spectra, stitched across instruments, hinted that water had begun to close the gap. Carbon dioxide remained the louder voice, but the ratio narrowed in a way that made the old thumbnail sketch of a layered crust feel plausible. A radiation-hardened skin venting CO2 first, then deeper reservoirs offering H2O as the thermal waves seeped inward, and paradoxically continued to work even as the comet receded. A curve like that is neither exotic nor trivial. It gestures toward microporosity, tortuous pathways, thermal skin depths measured in centimeters and hours, details most summaries file under assumptions and move past. Here, they felt like the story. C2 never quite found its footing. CN held on. C2 lagged, keeping 3i Atlas anchored in the C2 poor ledger lines that taxonomists draw to make sense of diversity. I kept reminding myself that depletion is a comparison, not a confession. You declare a ratio low against a distribution built from comets born under very different suns. Perhaps that is the point. If 3i Atlas was assembled in a nursery with a colder carbon chemistry, we should expect our yardsticks to mislead us. Normal is an artifact of sample bias, and the solar system is a sample of one. Nickel, more than any other thread, resisted closure. Robust lines at distances where heat alone is unpersuasive. Iron late and faint like an understudy no one called. The carbonyl route remained the least contorted path through the data. Volatile Ni, CO4, and Phi, CO5, forming in a primordial disk, surviving exile in vacuo, then photolysing into atoms our spectrographs can count. It isn't romantic, but it is falsifiable, and that's better than romance. I watched the modeling community walk a narrow ridge, parameter choices on one side, laboratory cross-sections on the other, trying not to slip into speculation. When two reductions from different teams landed within a tolerance tight enough to share, I underlined the page. Not because the case was closed, but because it was finally testable. Hints of rotation crept from the footnotes toward the text. The microsecond radar irregularity that no one trusted enough to headline. The shy periodicities in polarization that suggested dust grains aligning and realigning under a mechanical beat. The faint phase-dependent asymmetry in the inner coma that grew and faded with a rhythm too tidy to be random. None of it would clear the peer review bar on its own. All of it together felt like an instrument tuning quietly behind the curtain. A nucleus that tumbles faster than we assumed would help explain why lines brightened in one geometry and sulked in another, why depletion looked like a property on Monday and a perspective on Thursday. Meanwhile, the sky imposed its own editorial choices. We never got a single uninterrupted time series with uniform aperture, uniform phase, uniform slit. We collected shards and asked them to behave like a mosaic. They did, mostly. Where they didn't, I tried to resist the gravity of neat narratives. A green coma with weak C2 can be four different things: dust continuum in a helpful phase angle, overlapping molecular bands our resolution can't separate, transient jets that bias a slit, or the honest signature of a chemistry that doesn't care about our categories. The discipline is not to choose prematurely. What then do we keep? I keep the orbit. Interstellar, hyperbolic, precise. I keep the headline chemistry, a CO2 forward coma, that puts 3i Atlas among the outliers we have learned the most from. I keep the carbon chain story in pencil. CN present, C2 shy, classification useful but provisional. I keep the metals with asterisks, nickel early, and often, iron reluctant, a pattern that asks for carbonyls until a better idea pays rent. I keep the geometry lesson that conjunctions give and take in equal measure, and I keep the humbling truth that most anomalies shrink when cadence improves. What do we let go? I let go of drama about alien sails and steering whispers. Gravity did not ask for their help. I let go of the expectation that interstellar means unprecedented at every turn. Sometimes it means familiar physics with unfamiliar parameters. I let go of the impatience that wants a final page before the middle chapters have been written. There are, of course, the hooks I won't put down. If the CO2 on H2O curve truly flattened more than a simple thermal model predicts, what microstructure or chemistry is weaning the nucleus off carbon dioxide so slowly? If C2 remains quiet while color persists, which blended bands or dust properties are we undercounting? If nickel keeps outrunning iron, is that a primordial fingerprint of a disk we'll never see again, or a selection effect in our instruments that coincidence dressed as a clue? And who, exactly, had the cleanest line of sight during conjunction, and what did their pipelines discard as non-optimal before a human could decide what mattered? I find myself returning to first principles that feel like closing lines. We don't study comets because they answer us, we study them because they refuse. Interstellar objects remind us that our chemical expectations are provincial. A ratio that looks wrong at first glance may be the most honest thing a telescope can show. In a field notebook I'll carry into the next dawn, I've written a sentence I wish I'd written sooner. Treat every anomaly as a measurement of our ignorance first. Whether 3i Atlas will teach us a new chemistry or simply widen the error bars on the one we have, I'll let you decide. What I know is this. In a season of short nights and long reductions, the comet kept its appointment with gravity, displayed a composition our models can almost but not quite explain, and left behind a shape in the data that looks less like noise and more like a signature. The rest is out there now, folded into distances we can compute, and a silence we've learned to read. If the numbers start to behave, it will be because we learned to listen better.